Hey everybody, Delfeld here. It is Wednesday evening. I wanted to make a recording of the notes that we did today during class, like I mentioned. For two reasons, I wanted to put it up in case people wanted to come back and refer back to it, because there's a lot going on. It's very involved, a little more, intense, I guess you could say. And I also want to put up for people that may have missed it when we were in class, because it kind of takes a lot. There's a lot going on, and so I wanted it to be available to you. So I'm just going over what we did in class. So if you got that down with no issues, then maybe you don't even need to watch it. But tomorrow, which will be Thursday, we will go over another example, and we'll continue practicing on this. So if you didn't get it the first time, don't worry. We're going to have some practice with it. It's going to be challenging, but I think with a little work, you'll figure it all out. So we're talking about ionic bonding, and we're starting to draw or depict ionic bonds by using these Lewis dot models. Okay, and the first one we're going to do involves bonding potassium with sulfur. Okay, potassium is over here on the left side of the periodic table, over here, making it a metal. Remember, all these highlighted ones that you see now, those are metals. So potassium is our metal. So I'm going to put metal right in here. And then sulfur, you'll find over here on the right side, on the non-metal side of the periodic table. So sulfur is a non-metal. Okay. And that's what an ionic bond is. Remember, an ionic bond happens between a metal and a non-metal. All right, it's always between a metal and a non-metal. All right, so it has to be something from the left side of the periodic table and something from the right side. Potassium's got one valence electron. It's got one dot in its Lewis dot model. And we knew that, or could have predicted it, because it's in column 1. So shouldn't be a surprise. Sulfur is in column 6. Remember, so that should indicate that it's going to have 6 dots, which it does. All right, 6 valence electrons, 6 outside electrons. Now you start doing this by just dragging one of each Lewis dot model in. So I'm going to drag a potassium in, and I'm dragging a sulfur atom in. And remember, this is an ionic bond. An ionic bond takes place when electrons are transferred, when electrons are given away from the metal and they are taken by the non-metal. Remember, metals always have 1 or 2, maybe 3 valence electrons, so it's easier for them to just get rid of those electrons. They just want to unload those electrons and let somebody else take them. Non-metals, on the other hand, will usually have 7, maybe 6 or 5 valence electrons. And so it's easier for them just to pick up a couple additional electrons. And so that's what you're going to see right now. This potassium has one dot, one valence electron, and it's just going to want to kick it out. And sulfur is over here in need of 2 more, because it's got 6, right? Remember, the magic number we're always talking about is 8. So potassium's going to kick this one out. And guess who's there to scoop it up? The sulfur. Now, I made this so that you can use this little arrow. You should have just been able to drag the arrow, but I messed up in making it. So with this slide, you can't do it. In the future slides that we do later on, you'll be able to do it. So for this one, you just have to make your own arrow. You just come up here to the arrow tool, the little line tool, and you're going to choose an arrow. And you just want to make an arrow to show that that blue dot, that blue electron, is going to get kicked out and sent over there. All right. Now, this is kind of unnecessary. It's just because I don't like how it looks. I'm just going to make that arrow a little beefier, a little chunkier, so it looks a little bit better to me. So we have this potassium. It wants to kick that electron out, and it's going to do that. Sulfur is there to scoop it up. But that only solves half of our problems for sulfur, because it started with 6. It showed up to the party with 6 electrons, 6 valence electrons, 6 dots. And now it just gained 1 more, but that just brings it to 7. It needs 1 more. We can't just magically create an electron for sulfur. It's got to come from somewhere else. And it's going to come from another potassium atom. So if this is all going to work, you're going to need 2 potassium atoms. In order for sulfur to successfully bond and follow this octet rule to have a full outer layer of electrons, you're going to need, it's got to scoop up 2 electrons from somewhere. And so in this case, we're going to have 2 potassiums. So we need another arrow to indicate that the electron is going to transfer from that potassium over to the sulfur. So I'm just going to copy and then paste that arrow I made a second ago, and we're going to send it over here. Okay, because that potassium is in the same position as the other one. It wants to kick it out, and sulfur is in need of one more. So it's like, we have these 3 people at a party. Sulfur needs 2 electrons. In walk the potassium twins, and they have these electrons they don't want. They want to get rid of them. They want to unload these electrons, and sulfur's there to say, yeah, I'm going to take those. I need those. You guys don't need them. I need them. So that's how this all happens. The potassium atoms will get rid of those electrons, and the sulfur will scoop them up. When we come over here to the other side, we're going to draw this a little bit of a different way. Where this is over here, this is kind of the end result. Okay, this is the product, if you will. Now, in these brackets are some text boxes. All right. In these text boxes, all you need to do is put the symbol for the elements that we're working with. You got K for potassium and then S for sulfur. Okay. Now, in front of each of these brackets is another text box that I'm clicking now. Those text boxes are for a number, and that number is just the amount of each element that you have. So I got 1, 2 potassiums, so I'm just going to put 2 right here. That 2 is a coefficient, much like the coefficients you work with in algebra. When you have an equation like 2x plus 4, the 2 is the coefficient. Coefficient is just some number in front of a variable. Okay, 4x minus 6, the 4 would be the coefficient. It just tells you how many times x shows up. Okay, so this 2 is just telling us how many times potassium shows up. It tells us how many times potassium's there. It says how many potassiums are present. There's 2. There's only 1 sulfur, right? There's just 1 sulfur there. So we don't need to put a number in, because if we wrote it, then there must be a sulfur there. We don't need to say that there's 1 if we wrote it already. We can just assume, well, it's written there, so there must be 1. Just like in math, if you were going to write 1x, you don't have to write the 1. You don't have to include the 1, because the 1 doesn't change anything. So we don't need to put a number in front. So you just leave it as S, as sulfur, because the S is there. It's implied that there is at least 1 there. Now, if you had 2 of them, or 3 or 4 or 76, then you'd have to put a number in front. But since there's only 1, we don't need to worry about it. The next thing we need to include are some dots around these symbols, much like in the Lewis dot models we've created. However, we don't need any around the potassium. If you're wondering why, well, what do we just do with those electrons? Potassium just unloaded those electrons. It just kicked them out. It doesn't have them anymore. So we want to reflect that. We want it to show that potassium just cleared out its outside valence energy level of electrons. So we don't need to put any dots around potassium, but we do need to put them around sulfur. So you want to put them in. I'm going to put them in kind of quick by holding shift and moving them to where I know they need to go. So you're just putting them in the exact same format and the exact same position and setup as the previous Lewis dot model. So just like you see here. Okay, so there are the 6 electrons, 6 valence electrons sulfur showed up to the party with originally. But it's not done. What do we need? Well, we got to add in these 2 that it just gained. So I'm going to pull in 1 of those potassium electrons it got, and then the second one it got. And that looks a little more like it. Looks better. These boxes up here is where we're going to put a charge, because they're no longer neutral atoms. We had a change in electron amounts, so they're not neutral atoms anymore. They're going to have a charge to them. And potassium's a metal, and like all metals, it got rid of electrons, so it's going to become positive. Each potassium on its own got rid of 1 electron. That brought the electron count down, so the protons were winning by 1. Protons are positive, so the charge of a potassium ion is positive 1. Okay. Each individual potassium ion is now having a charge of positive 1. So this potassium becomes positive 1. This potassium also becomes positive 1. The sulfur, well, sulfur scooped up 1, 2 extra electrons, so it's going to have a negative 2 charge. because it's got 2 additional electrons. Electrons are negative. So the overall charge of the sulfur ion is -2. And that right there is our Lewis dot model for an ionic bond between potassium and sulfur. There's a few additional things we got to throw in, though. A formula. We got to put in a chemical formula. And that formula is just like the chemical formula for water. Water's chemical formula is H2O. It's H2O because there's 2 hydrogens, 2 H's, and 1 oxygen, O. So that's what we're going to throw in down here. We're going to put a K for the potassium we're working with, and then an S for the sulfur. And since there were 2 sulfurs, like we wrote earlier, and like we see right here, 1, 2, this little box down here is for a subscript number. Subscript is just numbers or text that's written kind of below the main line of text. So I put the 2 right there because there's 2 potassiums. Do I need to put anything here? No, I don't. I don't need to put anything because there's only 1 sulfur. We don't need to put a 1 if there's only 1 of them present because it's implied. If you wrote it there, then there must be 1. But if there were 2 or 3 or 4 or 8,456, then yeah, you'd have to put a number there. Okay, so you have your formula for this compound, for this ionic bond, K2S. So K2, kind of like H2, H2O. There were 2 hydrogens. Well, there's 2 potassiums. 2 hydrogens and then 1 oxygen in water. Well, there's 1 sulfur. So it's written a lot in a kind of a similar way. The very last thing we got to throw in is a chemical name. If you think back to when we talked about it originally, it doesn't get a very fancy name. It just gets something that's named a little differently or spelled or written a little differently. So the name is potassium sulf, and then it's not potassium sulfur, but for a name for an ionic bond, you always change the ending of the nonmetal. You always change the ending of the nonmetal to "ide." So the name of this compound is potassium sulfide. Kind of like we talked about, salt is sodium chloride. And like CO2, for example, is carbon dioxide, right? So when you change the ending, or when you're naming an ionic bond, all you need to adjust, all you need to change is the ending of the nonmetal. Because now it's not just potassium atoms and a sulfur atom. They've come together to create a compound that by way of an ionic bond, and we call that potassium sulfide. Okay, so tomorrow, or maybe you're watching this at a later time, on Thursday, the 18th of February, we are going to look at some more examples, get some more practice in, and with a little work and a little practice, I think it'll eventually click for you.